As a result of the differences between linear and nonlinear systems that we have discussed in the previous videos, there are some phenomena that you may observe in nonlinear systems which you do not have in linear systems. As we have seen, the behavior that the nonlinear system displays depends on the initial condition. And as a result of this, in nonlinear control systems, the stability that the system displays may depend on the magnitude of the reference signal. While for linear systems, we either had asymptotically stable behavior, unstable behavior, or marginally stable behavior, and which of these behaviors that the system displayed did therefore not depend on whether the system started close to or far away from the equilibrium point. In other words, there was no difference between the local and the global behavior when it came to the type of stability that the system displayed. Take for instance the control system given by this Simulink diagram here, where a second-order process is controlled by a valve. The valve has a nonlinear characteristics that looks like this. The flow out of the valve is the square of the valve input. And the valve is turned by a motor controlled by a proportional feedback controller. We will now give different reference signals to this control system. The initial value is the same in all three cases. We see that when the reference signal is 0.1, the system displays a nice asymptotically stable kind of behavior, and the system output converges to the reference value. This is a kind of behavior that we like to see in our control systems. When we increase the reference signal to 1, however, the system starts to display a quite oscillatory behavior. It still seems to converge towards the reference value of 1, but this takes a long time and the system oscillates a lot, akin towards a marginally stable system behavior. And when the reference is increased to 1.72, the system displays an unstable behavior in the sense that the output takes off towards infinity. So the stability behavior that the system displays depends on the magnitude of the reference signal, and this is a phenomenon that is only found in nonlinear systems. The type of stability behavior that the system displays may also depend on the initial conditions. In these simulations, we use the same reference signal and we vary the initial condition instead. In the first case, the initial value of the state x, which is the same as the system output y, is 0. In this case, we see that the system output converges nicely to the reference value. When we increase the initial value to 0.15, the system oscillates a little more, but it still converges quite nicely to the reference value. But when the initial value is increased to 1, the system displays an unstable behavior as the output goes to infinity. Later in this course, you will learn about the region of attraction, which is the set of initial conditions from which you can guarantee that the system behaves in a stable manner, converging to its reference values. Another phenomenon that you may observe in nonlinear systems, which you do not have in linear systems, is that of a stable periodic solution. These solutions are called limit cycles. We can create oscillations in linear systems as well. You know from linear systems theory that if you perturb a linear system by a sinusoidal input, then the system output will oscillate. Specifically, if the input to a system with transfer function h of s, the sinusoid u with some amplitude capital U and some frequency omega, then the stationary system response ys to this input is a sinusoid that has the input amplitude u scaled by the magnitude of h evaluated at S being j omega, where omega is the frequency of the input signal. The sinusoidal output oscillates at the same frequency, but with a phase shift, which is the angle of h of j omega. So we can make linear systems oscillate, but what is special about limit cycles is that they occur without any external periodic input. We can also have periodic solutions in linear systems without any external input. Remember that we got periodic solutions in the case when the system was marginally stable. For two-dimensional systems, these could look something like this, with the equilibrium point at the origin and periodic solutions surrounding the origin. But note that the amplitude of these oscillations were given by the initial value. If we started here, we would get the amplitude of this periodic solution, while if we started here, we will get another amplitude of the oscillation. Limit cycles, on the other hand, has both frequency and amplitude independent of the initial state. And in the case when the limit cycle is stable, the trajectories surrounding it converge to the limit cycle. So, if the system starts at an initial value slightly outside the limit cycle, it will converge to the limit cycle. And oscillate at its frequency and amplitude. And the same happens if it starts inside the limit cycle. And this is something that we can never get from a linear system. Therefore, in practice, if we want to create stable oscillations, we must use a nonlinear system. You can confer with your textbooks on electric circuits and see how they tell you to design an oscillator. One well-known example of such an oscillator is described by the Van der Poel oscillator, which was proposed by the Dutch electrical engineer and physicist Balthasar van der Poel while he was working for Philips. This oscillator can be described by the Van der Poel equation, which we can see here. It describes a circuit with a resistance, an inductor, and a capacitor, and where the resistance element is nonlinear. An intuitive description of why this circuit produces stable oscillation is that, depending on the value of x, the sign of the resistor coefficient here changes. When x is larger than 1, the sign of the coefficient is positive, because what's inside this bracket here is positive. And the resistor element thus consumes energy. When x is smaller than 1, the sign of the resistor coefficient is negative, and the resistor element generates energy. And it is this transition between alternately consuming and producing energy that generates a stable oscillation. We can simulate the system behavior using this equation with epsilon being 0.1, for instance, and we then get these results showing the time evolution of x. In the simulations, x is denoted by x1, while dot x is denoted by x2, and the initial value of dot x is 0 in all these simulations. The first simulation shows that when the system starts at x being 0.2, the system will start oscillating with larger and larger amplitudes until it reaches the limit cycle, where the amplitude of x is 2. When the initial value of x is 1, the same happens. The system starts oscillating with larger and larger amplitudes until it reaches the limit cycle. And in the last simulation, the initial value is well outside the limit cycle and well outside my coordinate system. And then the value of x decreases until the system state reaches the limit cycle, and then it starts oscillating with the same amplitude and frequency as in the two previous simulations. So we see that we get the same frequency and amplitude independent on the initial conditions, and this is something that never occurs in linear systems. Other phenomena that you may have in nonlinear systems and which never occur in linear systems are chaos and bifurcations. These are not topics in this course, since these kinds of behavior are something we typically do not want in our control systems, but I will mention them briefly. Bifurcation means that the system behavior changes character with only small changes in the parameters of the system, while for systems with chaos, the system behavior changes character with small changes in the initial value. One example of the latter is found in the system described by this differential equation here. We see that it resembles a linear second-order system perturbed by a sinusoidal input, from which we would expect a sinusoidal output in steady state. But then the system has this nonlinearity here as well. And because of this simple nonlinearity, the system demonstrates chaos behavior. We can simulate the system with almost similar initial conditions. In the first case, which is shown in black here, the initial value of x is 2 and .x is 3. While in the second case, which is shown in red, the initial values are slightly increased to 2.01 for x and 3.01 for x dot. And even if the initial values are almost the same, we see that the behavior here is quite different in the two cases. This was a very simple differential equation, and still it displayed chaos behavior. We find chaos effects also in the complex models describing meteorological systems. A well-known example of chaos behavior in such systems is called the butterfly effect. Due to the nonlinearities in the weather processes, a butterfly flapping its wings in Asia somewhere can produce a tornado in Kansas. So the small change in initial conditions is the tiny motion of the butterfly wings stirring the air around it, and due to the nonlinearities of the weather system, this can be magnified into a tornado.